Today we're going to have an overview or a brief go through of what are the common topologies for multi-level inverters. We'll be restricting our topic to say voltage source based multi-level inverters, and we'll look at the which are the most prominent ones. So if you see the contents, we'll have a very brief introduction, a working principle, then three of the most prominent ones: the diode clamp, the flying capacitor, and the cascaded one, that two in cascaded half bridge mode, multi-level inverters. We'll be looking at some very specific modulation techniques. What are the features of multi-level inverters? What references have been used to compile this presentation, and what's in store in terms of job opportunities? Okay, multi-level inverters. What are they? And so as I said, multi-level. We'll be restricting our topic to voltage source one. So multi-level voltage source inverters, they have surfaced as a different class of, power converters, inverters, options for high power applications. What it does, it typically synthesizes a staircase voltage waveform from multi-levels of DC voltages, right? So what you try to do basically do is have a power electronics converter or an inverter where you want to synthesize something that resembles a sinusoidal waveform. And when you do that, by using a multi-level inverter, you can actually do it by having it in steps. And as you see in figure 1, you see a stepped waveform. So that is what we basically do when we talk about multi-levels. A major limitation is the voltage unbalance between different levels. The methodologies that offer to balance the voltage difference between the different levels normally involve, some way of voltage clamping or capacitor charge control. We'll see this a little more in detail. So there are different ways to implement a voltage balance in multi-level converters. We'll go through some of the most prominent VSI ones: diode clamp, flying capacitor, and cascaded one. The basic operation of semiconductors will be shown by an ideal switch, which has several states. Switching patterns and switches and the commutation allow for the addition of the capacitor voltages, which will behave as, say, a separate DC voltage source, and the switches should be able to withstand the voltages of those capacitors, or say those DC voltage sources, right? So if you look at figure 2, if you see the very first figure A, that's just a conventional 2-level one, where if you measure the output from point A to either you are at, say, plus VC, or you are at 0. Whereas if you look at the second one, figure B, you now have split up your, say, DC source or your main. You've used the split capacitor principle, and then now you have 3 states. So if your point A, where you see this arrow VA, is connected to the top, you'll get the positive of that, which will be, say, in this case, VC. If you go to the middle one, you get what we call it as the neutral point. If you go to the bottom one, you get the negative of the voltage. And so this is just a 3-level. So you can extend a 3-level to, say, an N level or an M level. And what you do is basically you somehow split up these sources. So here, what we shown in our illustration is that you have split up the capacitors values to obtain different voltages, and then your output switch depends on where you connect, and depending on where you connect, or say in semiconductor technology, to which one you switch over to, will depend, and that will give you your output voltage. So this is just what I explained. Figure 2B is a 3-level inverter, since its output can have 3 different values. If you can go further to an N number, or say an M number of possible output voltage levels. That will be figure C, what we just seen. And you can, the purpose of going to a higher level one is that if we increase the number of levels, the output voltage waveform will consist of more steps. And this in turn will reflect a lesser harmonic distortion. So why you want to do this is because you want to, have a more sinusoidal waveform at the output, be it voltage or current. And the more you go towards a sinusoidal output, the lesser will be your harmonic distortion, lesser will be your losses, greater will be your efficiencies, which are some of the common things that we look for when we design an inverter or a converter from a power electronics point of view. So it's good. You can say I can have so many levels and I can go very close to a sine wave, but it's not that easy. On the contrary, the higher the number of levels, the complexity also increases, and hence are likely to introduce voltage imbalance problems. So that means, if you want to reach 10 volts, as your peak, and you have, say, just you want to do it in 5 steps. So you have, 2 volts each. The other way around, you can have lesser levels and say, I go in steps of 2, have 5 volts plus 5 volts to give 10 volts. But so that means that looks much easier to control, but you want to have a better, sinusoidal approximation. So you reach 10 volts by having voltages of only 2 volts and have 5 such of them. So that means you have to be exactly 2 volts. You cannot be 2.1, 1.9, so voltage imbalance problems are likely to rise along with the number of switches. So we'll be looking at some of those aspects when we look at say the pros and cons. Okay, so the first one is a diode clamped multi-level inverter. So we're going to restrict our topic to the 3 most prominent ones along with a 3 level, so that the concept is basically, you understand the concept, and once you understand, you can obviously then start extrapolating. So what we do in it's called a diode clamped inverter, or it's also called a neutral point clamped inverter. So again, you have a DC voltage, VDC. So you have a VDC, and then you split the voltage into half of that, VDC by 2, VDC by 2. Function of these 2 capacitors, you have the point, which is what we call the neutral point. You have your semiconductor switches, IGBTs nowadays, low power applications, MOSFET, still perfectly fine, no issues. GTOs no longer being used, So you have basically 4 IGBTs to get a 3-level output. So you have S1, S2, S1 dash, S2 dash, and you have this diodes D1 and D1 dash. Then we'll come to the switching table on how it works. There are 2 ways of measuring the voltage output. I mean, some people, for some references, they measure between, say, point A and point O. But usually when we talk about neutral point clamp, you measure between A and O. I mean, that's the whole purpose. You're measuring with respect to the neutral. Let's see, let's go into a little bit more detail. So the figure in this circuit, as I said, 2 bulk capacitors in series, C1 and C2, will divide the DC bus voltage. The midpoint of the 2 capacitors is the neutral point, and hence the output voltage VAN will have 3 states. You can have VDC by 2, minus VDC by 2, and the neutral itself 0. Now here, when you want to have neutral, have S2 and S1 dash on. Thereby, you're feeding the neutral to here, and hence the name neutral point multi-level inverter. When you want VDC by 2, what you'll have the top 2 switches on. So when the switches S1 and S2 are turned on, the output voltage VAN is VDC by 2. So basically, you're pulling this voltage right down to here, via S1 and S2, and you're measuring again with respect to the neutral. So you get VDC by 2. Vice versa, these 2 switches S1 and S2 are open, the bottom 2 switches are on, and you will get the voltage minus VDC by 2. And as I mentioned in the first place, why it is called, say, neutral clamped or say diode clamp is because you have S2 and S1 dash on, which will give you the 0 voltage. This, what you see on the right hand side, the graph, this, for how long duration you want to control this level depends on how long you control these switches, basically. That goes on to then the control methodology of it, which we will not look in detail so much right now. Yeah, so the major components that differentiate this circuit, basically it's the diodes, right? The clamping diodes, which will also, you can say, clamp the switch voltage to half the level of the DC bus voltage. It's a 3-level one. So we have, VDC by 2 minus VDC by 2 and 0. So this will again clamp you to that level. Just in case if you're measuring with respect to O, now this is okay if you do it because you have a single phase and you have this terminal available from you. But when you usually go for a 3-phase, there will be, say, 3 more such legs in which you're really not concerned about this point O. So in this case, if you turn on say S1 and S2 and you're measuring with respect to O, then you can say that I have this point, which is, say, effectively at this point, and I'm measuring with respect to O. So that will, you're basically measuring nothing but the whole VDC, right? So in this case, you can also say that D1 dash balances the voltage sharing between S1 dash and S2 dash, and S1 dash at the same time can be, blocking the voltage across C1 and S2 dash blocking that across C2. But as I said, in neutral point clamp, it's generic to use A and N. Yeah. So note that the output voltage so another point which a lot of eminent authors say that VAN is AC, and if you're measuring with, at the points A and O, or say A and 0, it's a DC voltage. The voltage across C2, which is VDC between, say, AN and AO. If the output is between A and O, a lot of people also call it a type of DC-DC converter, which will have 3 output voltages. So you can have half of it, full of it, and if none of the switches are in operation and you're measuring from A and O, it will be a 0. Just now moving on to the next prominent one is the flying capacitor one. So here what you do, you remove the diode basically, and you put in a capacitor. So again, from comparison purposes, again, we go with 3-level. Waveforms will also be similar. The number of switches you see, they are also the same. The way you are obtaining the neutral point is also the same. The difference here is that you are putting in a capacitor and removing the diodes. And this capacitor is basically called your flying capacitor. And hence the methodology or this topology is called flying capacitor multi-level inverter. Again, concentrating on voltage source. Operation will be very similar, as we will see. So figure 4R, again, it's a single phase, or say we're just looking at one leg of what can be extended to a 3-phase one. Here the independent capacitors, say, clamp the DC voltage to the capacitor voltage level of one of the capacitors. Again, 3-level output. You can be at, if you have, say S1 and S2 on, you can be at VDC by 2. If you have the bottom 2 ones on, you can be at minus VDC by 2. And if you have the middle 2 ones on, S2 and S1 dash, you are at a 0 volts. It's very tricky. It's easier to say that, keep S2 and S1 dash on. You still have a load from A to the neutral point floating. But if you have to really look at the modulation techniques in detail, and there are techniques which keep the capacitor voltage to a proper level. And if it's fully charged and you turn on S2 and S1 dash simultaneously, that's it's like a dead short across the capacitor, and you will result into blasting of it. So usually what you do when you make switching tables, you look for redundant states and which will keep your capacitor in a charged state the way you want it. So as I said, VDC by 2, both S1 and S2, need to be turned on. For the negative VDC by 2, the lower 2 one, S1 dash and S2, need to be turned on. For the 0 level, you can say S1 dash or S2 dash, they can be on. This is the point that I was emphasizing. The capacitor is charged when S1 and S2 dash are turned on, and it's discharged when S2 and S1 dash are turned on. So if I just go back, S1 and S2 dash will turn it on. So you say S1 and S2 dash. So this will provide a path for, charging it, and the other combination will provide a path for discharging it, which is S2 and S1 dash. Because it's a capacitor, so when it will ever see when it sees the load, it will obviously, discharge. And so then again, you needed to charge it back to get it ready for the next. The charge of capacitor C1 can be balanced by employing the proper selection of the zero level switching combination. So as I said, there is a in-depth analysis on when you go for higher level ones and how you want to maintain the balance. And so there are, balancing algorithms also. A lot of techniques have evolved in that, a lot of algorithms. And coming to the most, popular one, this is the most popular one. It's say very easy to synthesize, easy make. The drawback that I see from this, or I guess all of you can say, is that the number of switches, because they're all half bridge inverters, and voltage they add up in series. So what you'd basically do is connect the output of one, say for example the output of this, you connect it like this in a series fashion to the other one, to the other inverter. So what you do, whatever voltage you get here, it goes down and gets basically added. This VDC gets added and here, and then from this top and this bottom basically is where you get the full voltage. A lot of switching states. I guess you'll get the presentation and go through it. Let me just explain you. So for example, if you want, say VDC right here, you turn on S1 and S4, right? Similarly here, so that this will give you this VDC of this inverter. Similarly, you want VDC of this inverter, then what you will do, you will turn S11 on and S41 on at the same time. So these 1, 2, 3, 4 you turn on at the same time. You should get a level superimposing these two voltages to twice of VDC. Very important thing that you must keep in mind, these are just simple like single phase inverters, that you cannot turn these on simultaneously, S1 and S2, like the same way S11 and S211. So when you use this strategy, when you go from S1 to S4 and then change over from S3 to say S2, you want to turn on, you have to consider your dead bands, so that it's not that while this is turning off and S2 is turning on and then there is some overlap time, and during that overlap time you can cause a dead short across this, and boom, it'll cause a blast. So you have to be very sure about that. So this is basically it. I mean, you switch from this to this to get, say VDC. And if you use these two at the same time, again, you'll get this, the VDC of the lower inverter also superimpose. They get superimposed, you get 2 VDC total. And there's one good thing that you can do about this. I'll give you an example when we just get near to that part. So you can go through in the detail of this switching table. You get VDC for one, get VDC for the other, and you get 2 times VDC. And similarly, the negative side. For example, you keep all of the switches open, you'll obviously get a 0 volt. And go through them in detail, try and understand. But what I want to emphasize on this is that you can get these levels. Obviously, the phase voltage, that is obtained by the addition of the voltages generated by the different cells. Each single phase will generate either a VDC, minus VDC, or 0. And similarly, the other single phase, what we have shown, will also generate this. So you can go, you can have VDC plus VDC, minus VDC, another minus VDC, getting you minus 2 times VDC. But what I'd like to emphasize on this is here you can also have something which is called asymmetric, because these are two different sources, right? So here this can be say 5 volt, this can be 10 volts. So you can get, 15 volts. It's not necessary here that you bifurcate your voltage. Here you are using independent sources. So it's not necessary that you keep 5 volt here and you keep 5 volt here. You can keep 5 volt here and you can keep 10 volts here. You keep, you can change this voltage. You can keep them according to your design. One thing when you do that, when you keep an imbalance like this, you have to also look into the ratings of your devices. If the lower one is say double than the top one, you have to double check the voltage rating also, that will they be able to withstand a higher voltage from here. But this is what we really like about this, that you can, since they're different sources, you can keep the voltage level that you want.